New images captured by the James Webb Space Telescope have surprised researchers. Rather than broadening our understanding of the universe, these images revealed a disturbing fact: our current physical understanding is not sufficient to explain the nature of the cosmos in its early stages, where the Big Bang theory reaches its limits. This forces us to consider new hypotheses about its origin. The question arises as to how the universe was formed in detail and why. This new discovery challenges even the most experienced astronomers. To find out more about the Big Bang and the revolutionary details of the discovery, let's recall the concept of the Big Bang itself. Contrary to common belief, the Big Bang was not an explosion in pre-existing space. Rather, it was space itself that originated approximately 13.8 billion years ago, along with matter and time, from an original singularity. In physics and astronomy, a singularity describes places where gravity is so intense that the curvature of spacetime becomes infinite. Today, after billions of years since the beginning of the universe, we find that our cosmic home is part of a fundamental process. For experts, this represents an intrinsic feature of the universe since its very existence, its seemingly endless expansion. However, it's crucial to understand that the cosmos is not expanding into pre-existing space, rather, space itself is constantly increasing in size. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first luminous celestial objects clustered together to form mature galaxies. However, how quickly these galaxies grew remains an unsolved enigma. An important clue emerged through the first images captured by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected a number of galaxies, some of which had already existed some 300 million years after the formation of the universe. However, compared to the galactic structures that developed millions of years later, these early galaxies remained considerably smaller and less massive. This fits perfectly with the scientific model accepted by researchers. The density of matter in the young universe was simply not sufficient to give rise to galaxies the size of those observed today. What began as the discovery of 6 bright redshift luminous spots from James Webb turned out to trigger one of the most significant astronomical crises of recent times. Although these newly discovered galaxies are similar in age to previously recorded galaxies, they are almost as massive as our own Milky Way galaxy. This has created an intriguing mystery in astronomical research. After examining a series of images captured by the near-infrared camera, experts identified the previously mentioned light sources. Using redshift, scientists calculated that the light from these objects took more than 13 billion years to reach our eyes on Earth. Consequently, we are dealing with structures that had already existed between 500 and 700 million years after the alleged Big Bang. By analyzing the characteristics of these structures, it was concluded that the Webb telescope had captured 6 extremely early galaxies in the image. Surprisingly, these galaxies were so massive that they defied conventional expectations of cosmology. Instead of finding the expected dwarf galaxies, structures were identified that were almost as massive as our own Milky Way galaxy despite having formed early in the epoch. If we continue to analyze the data collected by the James Webb Telescope, this gravitationally bound grouping of stars was already more than 10 billion times the mass of the Sun at that time, with one potentially surpassing the 10 billion solar mass mark. However, even if this possibility is considered, the mystery is not completely solved. Even in this scenario, there would be significantly more stellar mass in the early universe than previously assumed, posing a puzzle. The detected objects contradict virtually all conventional cosmological theories. Even if only one of these galaxies turns out to be genuine, it would challenge our previous assumptions to explain the existence of these structures. Furthermore, the density of matter in the early cosmos would have had to be up to 5 times greater than previously assumed to explain this phenomenon. Another equally mysterious explanation is based on the fact that these galaxies developed in a way that is still completely unknown to us. These discoveries and the debates surrounding the Big Bang are leading more researchers to move away from this theory. Many astronomers with alternative views are frustrated that they are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as unfounded eccentrics. However, it is undeniable that even experts who still defend the Big Bang theory are constantly faced with questions without clear answers. These questions include particular issues such as why and how 13.8 billion years ago did something literally come out of nothing. Can something really originate from nothing, or was there some triggering event, or was it all just a coincidence? Stephen Hawking pointed out that the concept of time as we know it began only with the Big Bang, therefore, this process could not have been triggered by something else or someone external. A similar controversial question relates to the uniformity of radiation and density throughout the cosmos. No matter in which direction or at what distance we look on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Conservative scientists explain this phenomenon by the theory of cosmic inflation. However, other experts take this assumption further with a theory of chaotic inflation. According to this idea, it's possible that inflation has only stopped in some regions, like bubbles, and continues infinitely elsewhere. This implies that multiple universes form in these bubbles, each with its own individual physical laws. Within this model, a fundamental question arises: what if the cosmos does not represent the complete whole, and even more, what if another universe existed before ours? In that case, the Big Bang would become a part of a larger cycle. According to this perspective, our universe is part of a larger multidimensional structure. Within this model, the idea of an eternal cycle of collapse and rebirth of the universe is put forward. However, this is not the only perspective presented in the field of cosmology. Apart from the Big Bang theory, in 1955, for example, an article appeared in NASA's Cosmic Times arguing that there may have never been a Big Bang since the universe has existed for an infinite time. In this view, the expansion of the cosmos would be non-existent, and the continuous formation of matter could give the impression of a constant expansion of the universe. Another intriguing though controversial theory comes from the world of quantum physics and string theory. Supposedly, some experiments have suggested that our universe and everything in it do not actually exist. In simple terms, what we perceive as the visible universe could simply be a flat hologram projected onto a sphere. Therefore, there is a possibility that our reality is a result of a higher simulation. While this may sound like the plot of a fanciful science fiction movie, it can be connected to the Kardashev scale, which measures the level of development of a civilization according to its ability to use energy. If there were a Type 3 civilization capable of fully harnessing the power of an entire galaxy, it could have created a perfect simulation. However, finding out the truth in such a scenario is a very complicated matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The recent images captured by the James Webb Space Telescope have reignited discussions about the very fabric of our existence, challenging established theories and prompting scientists to reconsider fundamental aspects of cosmological understanding. At the heart of this inquiry lies the Big Bang theory, a cornerstone of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from an unimaginably dense and hot state, expanding rapidly and giving rise to space, time, and matter as we know it today. This cosmic event is not merely an explosion within pre-existing space but encompasses the very origin of space itself. The concept of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, underpins our understanding of this primordial epoch. Yet, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how quickly structures formed in the universe's infancy. These galaxies, detected within a few hundred million years of the Big Bang, appear surprisingly mature and massive, contrary to expectations based on current cosmological models. One of the fundamental questions raised by these discoveries is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within a fraction of a second after the Big Bang, causing the universe to expand exponentially. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, the recent findings suggest complexities in the early universe's evolution that may require revisions to inflationary models. The formation of galaxies such as those observed by the James Webb Telescope challenges cosmologists to rethink the conditions and processes that governed the universe's early epochs. These galaxies, already substantial in size and mass so soon after the Big Bang, imply a density of matter that surpasses previous estimates. The puzzle deepens when considering how such large structures could form and evolve in a relatively short span of cosmic time. Moreover, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up the majority of the universe's mass-energy content. While dark matter is thought to provide the gravitational scaffolding necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In parallel to these astrophysical mysteries, theoretical physicists are exploring alternative models of cosmology that challenge the traditional Big Bang paradigm. Some theories propose that our universe is just one among many in a vast multiverse, each with its own unique physical laws and constants. These ideas, stemming from developments in string theory and quantum cosmology, suggest a more complex and interconnected cosmos than previously imagined. One concept gaining traction is eternal inflation, where universes emerge continuously from a larger inflating space. This theory posits that our universe could be just one bubble among countless others, each with its own distinct properties. The challenge lies in finding observational evidence to support such speculative ideas as they push the boundaries of empirical verification. Another provocative hypothesis is that our universe exists within a simulated reality, akin to a computer-generated simulation. This idea draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with astonishing fidelity. If true, our perception of reality as a tangible physical universe could be fundamentally altered, raising profound philosophical and scientific questions about the nature of existence. Moreover, advances in observational astronomy continue to reveal the universe's vastness and complexity. Telescopes like the James Webb Space Telescope, with its unprecedented sensitivity and resolution, promise to unveil even more secrets of the cosmos. Future observations may shed light on the earliest moments of the universe, providing clues to its ultimate fate and the underlying principles that govern its evolution. Beyond observational astronomy, particle physicists are exploring the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central goal of theoretical physics. Theories such as quantum gravity and string theory offer potential frameworks for understanding these fundamental interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. The concept of time as a linear progression from past to future is challenged by quantum theories that suggest time may be emergent or even illusory at the fundamental level. Understanding the nature of time within the context of cosmological models could revolutionize our understanding of the universe's origin and evolution. Moreover, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope's study of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. In addition to these scientific endeavors, cultural and philosophical reflections on the cosmos enrich our understanding of our place in the universe.